All right. Well, thank you very much, everybody, for joining us this afternoon for this breakout session. I'm Maurizio Martinovic. I go by Ritz for short. I'm a senior product manager within the simulations technology team here at AWS, and I'm joined by Wesley Tannis from Lockheed Martin Skunk Works, who is going to be my partner in crime for the next hour for this session. Now, we realize this is more or less right after lunch, so our goal for this hour is not only to educate, but also to entertain and make sure that you guys all stay awake. But before we jump into things, I'm going to give Wes a quick opportunity to introduce himself and what he does at Lockheed Martin.
Thank you, Ritz. So as Ritz mentioned, my name is Wes Tannis. I'm with Lockheed Martin Corporation, which, if you aren't familiar, is a little mom and pop shop out of Bethesda, Maryland. You know, we build airplanes, we build helicopters, 100,000 people, not big. I work in the Skunk Works division, which is that little secret squirrel over there in the blue square, where we do all sorts of research and development projects. My particular focus is visualization, modeling and simulation, human-computer interfaces, bringing information to people in ways they can easily ingest. So Ritz and I teamed up for this product that he is going to explain to you.
Fantastic. So you may have heard or watched Sandy Carter's partner keynote from yesterday, where she mentioned how AWS is providing customers the capabilities to overcome scaling challenges with the cloud. And there was this particular slide from that keynote, and the one that we're going to talk and deep dive on today is the one in the middle here between, as one of our examples, Unity, Lockheed Martin, and AWS. And that's going to be one of the two demos that we're going to show you here this afternoon. Now, at Amazon, we have a series of leadership principles that some of you may be familiar with, and if you've spent the week at reInvent, you may have heard a lot about them. And one of them is called Think Big. And Think Big is about charting new and unproven paths, about thinking differently and driving innovation in new ways. So we're going to show you, over this breakout session, how customers are leveraging games technology in new and innovative ways to run massive simulations on AWS. We're going to talk about game engines, we're going to talk about multiplayer game frameworks, we're going to talk some geospatial data, and we'll even throw in some metaverse there for good measure. So we're going to start by giving you a vision of what it is we want to build, what we would call our end game. Our big, hairy, audacious goal, as sometimes that's referred to. Then Wes is going to jump in and give us an overview of what modeling and simulation and the practice of modeling and simulation at a high level so that we're all sort of level set. And then we'll discuss how those concepts relate back to games. We'll then show you two of our demos on how AWS is enabling massive scale simulations with over 1 million objects. And we'll close by looking into the future and the implications of some of the work that we're previewing here today. And so over this breakout session, we invite you to join us and think big with us as we give you a glimpse into the future of simulation powered by the cloud. Now, Wes, you and I were sort of reflecting on this the other day, and how all the way back in January and February, I sort of came to you with this idea, and I was like, let's just do something crazy. Let's build a simulation and put 1 million things on it. And would that be ambitious enough for you?
And the reality is that was a little bit too ambitious for some of the people that I work with. They thought we were crazy. Even when we brought in the power of the cloud, you know, using multiple computers, using cloud storage, they still thought it was a little bit ambitious to do 1 million entities. And we did it.
And I also had some people telling me that I was crazy. So if you have two sets of people telling that you're crazy, you're probably on the right track. And so we want to build a simulation with 1 million independent and dynamic entities. We want to put that in a real-world setting that is capable of being interacted with, visualized, and analyzed by multiple users in real time. And that's a mouthful. So you may be sitting like, wait, what? That's mind-blowing. OK, let's break it down a little bit. Let's break this down into 3 components. And then we're going to go through each one of these and show you how it's actually possible to do this with what we've built. So simulate 1 million independent and dynamic entities. And by that, we mean 1 million distinct things that change their properties throughout time. Now, if you're familiar with games, an example of this, like if you're playing something like Fortnite, is your avatar, your character in Fortnite. That would be an entity within the game. All right, so something that changes position, whereas something like a tree or a building within the simulation, we would consider that as a static entity, not as sort of important to us in this particular context. Real world setting. Basically, we need to be able to put this anywhere on the globe at any time. Yep. And interacted, visualized, and analyzed by multiple users in real time. Sounds challenging, because it is, but it also sounds a lot like a game.
It does.
So, 3 components that we need to build this simulation that we want to do. But what even is simulation, right? And so let's answer that, and then we'll get to the how of how we actually go about this. Wes?
All right, so yeah, what is a simulation? Well, a simulation is the evolution of a model or a series of models over a given period of time, which really doesn't answer the question, what is a model? So there are a number of different models, and I'll give a couple of examples here. We've got physical models, so one of the things that we do a lot to develop an aircraft is we will build a physical model of what we think the aircraft should look like. We'll put it in a wind tunnel, and we'll see how it behaves. That is a kind of model. Weather models are another one I studied pretty heavily in college. Let's take a computer model of how weather interacts, and let's put some new circumstances into it and see how the weather situation evolves over time. See if we can predict it. It's actually really difficult, and that's why you all think the weatherman is always wrong. Mathematical models. So does anybody want to make their physics professor in high school proud and tell me what this is? This is the equation for change in position. Delta x is v naught plus 1/2 at squared. Basically says that how far you move is based on your velocity and whatever acceleration you have. That's another kind of model. And then agent-based models are models where we have actual independent agents acting in them. And that sounds a lot like a game, doesn't it?
It does, and this is actually the really fun one. And it's going to be part of what the demos that we show.
So why do we even bother with simulation? And that's a really good question as well. You set up models, you test these models. Why do we bother with them? Well, it's because we want to test things that we can't actually do. So we'll talk later about a scenario where we're simulating disaster recovery in San Francisco after an earthquake. Why simulate it? Well, because inducing the earthquake would mean we'd have to actually recover from an earthquake. Also, I'm pretty sure the Senate would have a lot of questions for us if we were to create an earthquake in San Francisco, one of them being how. So again, it's a city of a population of almost 1 million people, 232 square miles. It's an excellent place to look at how we would mobilize first responders, how we would get supplies to it in order to recover from a disaster. Where would we put those supply locations? What would see the most damage? Who would we prioritize? They're not questions that we can easily answer without seeing the real thing play out. And San Francisco is really nice, and I don't want to ruin it. So we're stuck trying to simulate what that would look like. And the other thing is, you know, big disaster, you need a hero to save you from it. It's what the movies all say. Now, the copyright people at both Amazon and Lockheed Martin told us we couldn't use a picture of The Rock. So our hero is a rock.
It's a pretty good.
It's a really nice rock, but I don't think that it's going to save us from the earthquake. So, and also hope is a really bad strategy. So instead we simulate, and we simulate to try to understand how to recover from situations like this. Again, going into a little bit more of why do we do simulation? Well, the reality is we want to iterate quickly on these things that we want to do. We want to do them, you know, in less time than they would actually take. Actually, you know, fighting out a war in a war game could take months for the war to happen, but a war game, you know, takes a couple of days to run. We want to do things that are dangerous. You know, again, we don't want to start a war with another country just to see how our products work. We would much rather simulate that. We don't want to, you know, fly a bunch of aircraft into a hurricane without having tested it first. In autonomous vehicles, nobody really wants to step in front of the car that's been designed to stop if someone steps in front of it until we've proved that it will stop. Control is a big part of simulation as well. We want to be able to control the various inputs to this simulation and see what comes out of them. We want to be able to see what sort of multiple outcomes come when you tweak that little butterfly you threw in. And finally, it's just lower cost to do that. Aircraft take a lot of money to fly. $2,000 or a couple tens of $1,000s to put an aircraft in the air, maybe take me $100 to simulate that same aircraft. So we want to put all these things together, and the closer we can get our simulation to real life, the more useful the outcome is.
Right. Thank you, Wes. So that's the what and the how, and the why, rather. So what about the how? How do we actually make and run these simulations? So if you think back to the definition of the simulation, it's the evolution of a model over a given amount of time, or a given series of time. So how do we move time forward is the question here, right? Well, we do that with something called a simulation engine. And if we actually take this literally, that is an F-135 engine that will go into your F-35. But bear with me here, and let's get the analogy to keep going. We would take our models and put them into an engine, and then we can actually produce something that people can interact with, like the pilot here for the F-35, who jumps into the cockpit of the simulator, who can now run their mission, tweak some parameters, and see and actually carry out the mission so that when they get into the real aircraft, they can execute the mission and do so safely. Right? Now, we've talked about various different types of simulations, the physical models, the weather models, the kinematic models. But there's one type of simulation that's very special that we now need to get to, and that's games. Because in the midst of all the fun in the games, there's a lot of math and a lot of modeling that goes on behind the scenes to make the fun possible. And this happens as a result of the game engine that is running under the hood. So, for example, when I fire my weapon in Fortnite at my opponent, how do I know if I actually hit them? Or how do I know if they've hit me? And if I fire off a skill shot in League, which I'm not very good at, is it going to land? The answer is usually no. But the game engine will tell me. Games like EVE Online and New World are massively multiplayer online games with hundreds of thousands of concurrent players. And they've created simulations of persistent worlds that run their own economies, they have their own social norms, they have their own rules, and they have even their own conflicts. And so in one case, we're modeling physics. In the other case, we're modeling the various social constructs that make up basically human civilization. But in both cases, we do so over extended periods of time, right? Your Fortnite game may last 20 to 30 minutes. In the case of EVE, this has gone on for 18 years. And so let's dive in to an actual example of this and kind of see how it works. And for that, I'm going to leverage New World, which is Amazon Game Studios' latest hit game. And in the spirit of Thanksgiving, since that was last week, hopefully everybody had a nice Thanksgiving holiday, I'm going to go turkey hunting within the game. And so my avatar here in the game is going to sneak up on an unsuspecting turkey. I'm going to draw my bow and then attempt to make Thanksgiving dinner out of this turkey. And if we do this, what we actually see, if we analyze what's actually going on here, this is a combination of agent-based modeling and also mathematical simulation. Within the game, both me and the turkey can be considered agents or entities within the game, and we have some properties, right? We have a position, and we have some sort of health, and when the health of either myself or the turkey reaches 0, the game's going to end, unfortunately for one of us. And there's other rules within this game. How fast can I move? How far can I shoot? Where does the turkey go? Does the turkey avoid me or not? Right? And these are all being computed in real time. And I'm getting feedback as a player from the game server and from the game engine about what's going on in the environment around me, and I can interact with that. So we start with me standing here in a certain position, my turkey dinner on the other, and we run the clock forward. And now the simulation gets a bit more complicated because now I actually have to compute the arrow that I'm going to shoot has a velocity. The turkey is moving in a certain direction, and so we'll just use those lovely kinematic equations that we thought. And behind the scenes, the Lumberyard/Open3D engine that Amazon has recently open sourced is going to compute this all for me and tell me whether or not I actually hit the turkey, right? And that's kind of our objective here. And so if we go ahead and compute this, we move time forward again, the turkey is turned into dinner. Fortunately for me, unfortunately for the turkey. But it was quite good. I mean, in the game, you have to kind of feed yourself, so this worked out in my favor, right? Now, Wes, from your standpoint, you kind of see these simulations from perhaps a tactical standpoint, but you use, at Lockheed, you use simulation perhaps a similar but slightly different way.
Yeah, so there is a certain tactical element to this. You've got two entities here, the player and the turkey, both facing off in a tactical engagement. One of them is attempting to stealth through it. The other one is attempting to stop him from stealthing through it. Honestly, usually in war games, we don't use a bow. Despite what Civilization will tell you, they're not effective against stealth bombers. But they are very effective against turkeys here, as you can see that the turkey's health is now dinner. Be honest with us, Ritz, how many shots did this take you?
Well, you craft 50 arrows at a time, and the screen says that I have 38 left, so yeah. In any case, we're going to move off that. My poor aim is not the subject of the talk. Anyway, but it's the game engines, right, underneath that make all the fun possible. And so game developers used to spend all this time, a considerable amount of time and resources, developing their own engines, and some of them still do. But in addition to O3DE and Lumberyard, which we saw here, Epic Games and Unity have put together tremendously powerful toolkits and frameworks to help developers create amazing games, such as the ones we see here. This allows developers to focus on making highly differentiated content, finding the fun in their games, and giving them photorealistic rendering. And now we've seen a trend where customers are beginning to take the best from the games world and start applying that to the simulation world to simulate real-world systems.
Yeah, we're starting to see our customers coming back to us, especially as millennials start to enter the officer corps in higher and higher levels, going, you know, I've got this simulation that you made for us of when this aircraft had a mishap and whatever, and it's based on all this stuff that's from, 2005. Why doesn't it look like Ace Combat? Why doesn't it look like a modern video game? On top of the fact that these games are starting to get so close to realistic and starting to focus so much more on realism that they've actually got very, very good physics interaction engines in them that allow us to do fairly accurate simulation within the game engine without having to do any of the heavy lifting.
And so now what we have is this plethora of new use cases across various different industries, and the game engines are really being the bridge to connect the two worlds, the digital and the real world. And so why? Why would that happen? Well, because there's a lot to love from the games world, right? Which by our definition are simulations. They're a special type of simulation, but they can be just as complex as real world. By definition, they occur at large scale, with large numbers of distributed computing and hundreds of thousands of concurrent players, right? And that can all be interacted with. They occur in real time. They're highly non-deterministic because they're constantly taking user input, and they have a visualization component that results in often quite spectacular renderings, which we see one of them here, where we have in Unity a full 3D representation of the Earth. And you kind of love this globe.
Yeah, so we're zooming in right now into the Himalayas. Some of you may recognize the mountain that we're going to zoom into, but I'll give you a hint at the end. So this is our digital twin of the globe that we've been working on with Unity for quite some time. And the idea is to have this real world globe that we can pull into any of our products and just see what's there in the world without having to do any of the extra lifting. And if you hadn't guessed it already, this is Everest.
Yep. And so the same is also happening with Unreal, where we can simulate real-world environments. And as we see some of these applications within the defense space, and Wes, that's a space you're quite familiar with here. But we are also going to see applications in other areas, in other industry verticals. Pretty soon, we're going to see here a quick representation of the Unreal Engine here being used for autonomous driving. We also have various industrial applications where we're using 3D for sort of immersive education and learning. And there's also healthcare applications to this. And these are actually all areas that we're going to come back to here towards the end of the session. But if we go back to the decomposition of our problem, we actually now have the answer to one of the three pieces. We're actually going to work this a little backwards. So the interacted with, visualized, and analyzed by multiple users in real time is actually going to be solved by our game engines, right? Unity and Unreal. Now, on to the next piece. How exactly do we plan to create the real world. There's one way you could do it. We could go out and literally design, draw, texture, and shade every single building, every single tree, every single road in object in the world. And that would take forever.
How much money you got?
Not enough. Yeah, let's do something else. That's right. So if we did it that way, it would just like not happen. So in order to do this piece, we're actually going to lean in on being able to use highly accurate 3D geospatial data. And we have some fantastic partners that we've worked with to actually make that happen. The first one is Here Maps, and you're going to see this in more of Wes's demo in a second. We were able to get a 3D representation of San Francisco using Here's Premier 3D Cities data. And Premier 3D Cities is an index data set where each of the objects that you see here, like example in this picture, are their own self-contained digital volume, and the data supports sub-1 meter geospatial precision. So this gives us a way to create a realistic environment with a high degree of accuracy that we can import directly into the Unity engine, and we can also reuse it from project to project. You don't want to have to remake that globe every single time. Exactly. The second one is actually Cesium, who has developed an integration with Unreal that we will use to import highly detailed photogrammetry of Melbourne and Denver directly into the Unreal Engine. And this is sort of a high-level rendering of the city of Denver, which we're going to see in more detail in one of our demos. OK, so that solves the second one, is our 3D geospatial data with our partners here in Cesium. Now, how do we get the first one? This one is actually simulating 1 million independent and dynamic entities. Seems difficult, but where are we, Wes?
We're at a cloud conference.
We're at a cloud conference. We're at reInvent. All right, so this is actually the easiest answer you're going to see all day. This is AWS. Right? This is powered by AWS with a slight twist, because we're going to be leaning on the architectures and frameworks from massively multiplayer online games to get this one done. All right. So what had previously looked like a very difficult or impossible task is actually achievable with some elbow grease and hard work, because it did take us a decent amount of time to put these demos together. And as our favorite Captain Picard would say, things are only impossible until they are not. So to make the impossible possible, Wes and Lockheed Martin with the demo. Take it away.
Fantastic. And I apologize for how bright these slides are. Our background is white. So simulation is very critical to our business model. As I've mentioned before, it allows us to establish our capabilities and our credibility very quickly for our customer. It allows us to solve problems before they arise. For example, how do I get enough food to feed hundreds of thousands of people into San Francisco after an earthquake? It's a pretty big problem, pretty big difficult problem, and we want to solve that before it arises. And also doing things without having to do them. As I mentioned before, you know, flying aircraft is very expensive. Wars are something we want to avoid. So we want to be able to simulate these things before they actually arise without having to actually do them. Simulation traditionally takes a lot of time and a lot of space. The way we used to do it is one person with one view, taking a lot of time, hours to weeks of time to put together a simulation. But that's not where we want to be. Where we really want to be is many computers and many views, and doing it in a very short amount of time, with our end goal being this digital twin of the world that I mentioned. So tagging back to the San Francisco discussion, we wanted to show a good demo of this problem space and how to solve it. So starting with the idea that we want to demonstrate a simulation at a vast scale, which is not usually where we start our discussion, but bear with me. We want to visualize a lot of moving pieces, and we want to present it in a compelling manner. And we also want to do it here in reInvent, but also at ITSEC, which means we need something that's publicly accessible, something, you know, that makes everybody feel good about themselves. So obviously we can't do wargaming. And we have the really nice city from Here Maps. So San Francisco is our target location. Obviously that means we're going to do an earthquake recovery. So now we've got our dream team together. We've got the Lockheed Martin Skunk Works with our earthquake recovery scenario. We've got Unity with their engine design. We've got Amazon providing the muscle. How do we put all that together? Well, we scale it on the cloud. That cloud scaling allows us to increase our simulation scale from, you know, the traditional, we would have used maybe 10, 20,000 entities, up to 1 million moving entities. It allows us to bring together multiple users. If you happen to be at ITSEC in Orlando, which unfortunately none of you are, Orlando is lovely this time of year. The demo is currently running at 3 places on the show floor there, at the Unity booth, at the AWS booth, and at the Lockheed Martin booth. And of course, we wanted to reduce development time and complexity. This particular scenario we managed to accomplish in only a couple of weeks, with the development of the engine taking longer than that. So here's our reference architecture, and it looks simple and it looks complicated at the same time, and you would be right on both of those things. So it starts out with our data, the Lockheed Martin data set for various variations of this earthquake scenario and the recovery scenario for it. And that includes information on each of the shipments we're making, where they're going, who requested it, et cetera, et cetera. The mode of transportation, the route they're gonna take. It's a tremendous amount of data to analyze. But we can put that into an Amazon RDS and then distribute that calculation over 10 different compute clusters in the cloud, each of them running the Unity backend to do all that calculation. And we divide it up into geospatial divisions. So each of those 10 computers is responsible for a part of the United States that they have sovereignty over, and those calculations will all be done on that node, and they will pass them off as the entities move. Then it passes them over to the 3 Unity View application clusters, one for each of the views we have going on at ITSEC right now. And all that data is passed over the Unity client, combined with here maps and displayed to the user. That's a lot to say, but it comes out to a really pretty picture. So here's the demo, and with every demo, with every model, there's always assumptions you have to take into effect because all models are wrong, but they're useful if you understand why they're wrong. So with our demo, the assumptions to take into account are we're only doing logistics here. We're just looking at getting the supplies into the city. We're not looking at any sort of distribution yet. There wasn't enough time to add that sort of thing to this model. The trucks and the aircraft move directly from their warehouses across the country to the distribution point, one in each zip code in San Francisco. And unfortunately, the trucks in this model do not follow the roads. I know you guys are gonna look at the dots moving over the San Francisco Bay and think that Lockheed has invented a hover semi, and we haven't, and I'm sorry to tell you that we haven't. So here's the demo. Takes a little bit to get through the launch screen here, but you'll see shortly after the recovery begins, we start to get some of these dots moving from various cities. He'll zoom in here in a second. Moving from Los Angeles first, moving from Las Vegas, moving from Sacramento. It's requesting requesting supplies from all of these cities. Every warehouse in San Francisco has a level of supplies that it wants to keep. Food, water, medicine, and fuel, 4 things that we need to recover from an earthquake. And they are calling out to various FEMA warehouses across the United States. So once he zooms in here, you can see the packages flitting across the bay. Unfortunately, that's not how that works, but time is a factor that we had to consider. And of course, this very beautiful Here Maps 3D model that we didn't get to do too much more with. But he'll click on one of the warehouses here in a second, and you'll get to see the supplies bouncing up and down as each citizen consumes supplies and the warehouse calls out for more. And all of this data for number of citizens we assume are going to be surviving after this quake, where each zip code is, et cetera, was provided on the San Francisco City website. So this is all hopefully authentically sourced, even if the transit routes are not. So here you can see one of the cities. This is Denver, I believe, beginning to collect supplies for itself. And unfortunately, again, ran out of time. There's some spiraling here because we didn't have really accurate locations on where food, water, and fuel would come from in this city. But this city is providing shipments and sending them out via truck. And then just real quick for funsies, we've got a real quick scenario of how that looks and plays out over the course of 30 days. You can see that the West Coast cities deplete a lot faster because they committed a lot more resources up front, whereas after 30 days, the East Coast cities are only just starting to get into the supply mix. So with that said, I will turn it over to you, Ritz, to discuss the megacity.
Fantastic, Wes, thank you. And it's truly fantastic what the team was able to achieve in such a short amount of time. We put that together in about 4 to 5 months, which included the integration with Unity and their new 3D geospatial framework, which is really, really exciting. Let's quickly review a second use case here that we implemented with our partners Cesium and Unreal. From our previous demo, we saw that we had the ability to simulate on a continental scale. Wes had zoomed in on the city of Denver, Colorado, and you saw the dots moving into the center. Those were all Unity game objects that were actively being simulated within the Unity engine, and there's 1 million of them spread out across the United States. We could have zoomed in on any of the 30 cities within the US that were shipping supplies, and we would have seen something similar happen there. But what if we wanted to see what's actually happening on the ground? Well, we can actually do that too. So using the power of Unreal Engine 4 and our photogrammetry data, we've recreated the cities of Melbourne, Australia, and Denver, Colorado, and filled them with 1 million fully 3D AI-enabled Unreal actors. These actors path between different locations, they actively avoid one another, and they wander across the various Unreal Engine boundaries which we are drawing on the screen at the moment. And we have partitioned that out into the grid that you can see here. There is 10 C524XL instances that power this simulation and 160 Unreal servers that are running on those instances. This is a quick debug view of what the server sees. So there's actual simulation happening within these, this example. There are no ghost entities here, no ghosts. All the Unreal actors are real actors that are actually being simulated in real time. What this looks like from a top-down view, this is an overlay of the photogrammetry data with the spatial partitioning. Each square there represented in a different color is a spatial partition which is running an Unreal server process. Each server or instance of Unreal Engine 4 runs the same simulation logic. So when actors cross the boundaries, they carry on with the pathfinding that they were doing when they were in the previous one. And so all the actors behave exactly like you would expect them to. And from the perspective of somebody observing the simulation, it all looks like one seamless, persistent world. And that is really what we're going for. The reference architecture on this one is a little simpler. We basically have our 10 instances here running the various Unreal Engine servers. That data is then aggregated into one particular Unreal View agent that is looking at a particular area of the city, and then that View agent is sending that data over to the Unreal client, which has pieces of the nice photogrammetry data so that we have a nice visual representation on the client side of what everything actually looks like. But the Unreal Engine servers do have nav meshes that we generated from the Cesium data as well. And so that's how our entities are doing the pathing around the servers. And again, this is just sort of the high-level overview. There's the rows that represent each of the servers, and across we go from the Unreal instances. And this allows us to reach 1 million actors, true actors, no ghosts. Simulation at scale in the cloud. So after seeing those two, where do we actually go from here? Now, I was going to call this segment to infinity and beyond to just be like, you know, a scale thing, but Max Peterson took that for his leadership session, and he's a VP and I'm not, so he wins. So that title got axed. But Wes, where do you want to go from here?
Well, I mean, aside from combining those two simulations so that you can watch the individual actors each carry supplies back to wherever they're living and consume them, there's a couple of ideas, and the first one is healthcare. In the middle of a global pandemic, we could absolutely use technology like this to simulate the spread of a disease and to simulate how various mitigation efforts would slow that spread.
Yep, we could definitely do that. And you know, when you have large-scale sort of mega cities, right? New York has a population of 8.6 million, LA is 4, Chicago 2.6. You don't really want to tell a simulation engineer, well, pick 1,000 people and simulate them, because that's not really representative of the real world. And kind of going back to your point earlier, where the closer we can make things look to the real world, the more accurate they get. And that's both in terms of what the simulation looks like from the globe standpoint, but also in terms of the scale. And so you can see, right, the social distancing, the mask wearing, would that actually, sort of stop the spread of the disease?
And look into, across the continental scale, would travel restrictions help, or would certain other ideas help more to restrict the spread, or would they not?
The next one is one that you keep bringing up. It's your digital twin.
Yes, the digital twin, this concept of could be a city, could be, a vehicle, could be, any sort of thing that you physically have, building a digital twin of it, creating a virtual parallel San Francisco, or a virtual parallel F-35, or a virtual parallel oil and gas refinery, and simulating using that to train, to do logistics, to look into various scenarios of what would we do if this happened. There's a lot that you can do with this concept of the digital twin.
And if we even use some IoT concepts, right? All those shipments that we were sending in the particular simulation that we did with you guys, if you had actually put IoT sensors on those shipments, you could, if you were actually running the simulation or something did happen, you'd be able to get feedback in real time and data in real time of all those shipments in your logistics operation.
Yeah. And if you take that back to, what everybody expects from Lockheed Martin, the concept of military operations, IoT sensors on all of your individual, units, soldiers, whatever, it gives you this concept of being able to see at a very large scale and a very small scale where your units are and what they're doing.
The next one we wanted to bring up was, you actually touched on autonomous cars earlier.
Yeah.
This is a very interesting one, because you could conceive of, if we had this 3D geospatial data, and we had this globe, and we had cars, autonomous cars, that were just pumping out lots and lots of data and acting like IoT sensors, could we create a sort of, could we actually go into a city with our cars and test them, and you could see what would happen? But not just one car, a whole fleet.
Well, being an Angelino, the concept of trying to solve traffic is near and dear to my heart. I'm not really looking forward to the drive back to LA, but autonomous vehicles would certainly make that a lot easier. Unfortunately, the Rand Corporation's estimate of 275 million miles to prove that autonomous vehicles are as safe and reliable as people. How many years does that calculate out to?
100 AVs, 24/7, 365, 12 and a half years.
I don't have that kind of time.
I don't. I am ready to accept my robot overlords already, actually, too. So
Yeah, so why don't we just simulate instead and prove it out through a simulation rather than actually driving those cars around?
And it's going to not just simulation, but simulation at scale. And the scale that we're talking about today is going to be really important to reach those milestones in realistic timeframes. Then we started this talk by talking about games and then games technology, right? And then we moved over to the real world. And then let's take it back. Let's take it back to games, right? Because there's this amazing space where we see all this games technology developing, but we can also push it and push it to new limits here. So online multiplayer connected games started very similar to this. This is one of the original MUDs, the multi-user dungeons back in the 70s. Text-based, no graphics.
Yeah, the graphics are a little disappointing.
Little disappointing. This is not something like the kids play these days. And we've come a long way since, with games like New World that put thousands of players together in immersive worlds and engage in combat. But games are evolving too. And we see this with our partners in Epic and Fortnite. Just take a look at Fortnite and what it's done over the last several years, right? This was a game that had a single player mode that then added Battle Royale and just took off. But it's become so much more than that in the time that it's been around. You could take in a concert with Marshmallow or Ariana Grande within the game. You can catch a Star Wars movie, which they previewed for their players within the game. You could take in the new year and celebrate the fireworks spectacular. Or you could just gather all your friends and lay on the beach on your own private island, and everybody builds nice castles and forts. But there's so much here in creating a virtual world that transcends the game's shooter gameplay. And the limitation right now is that these experiences are still largely limited to about 100 players in a single game server at any one time. Even though there may be millions of them logged in, they're all in their discrete, separate worlds. But what if we took the same principles that we discussed today of this massive scale simulation and distributing this compute, and all of a sudden we went from 100 players to 1,000 players in the concert, to 10,000 in the concert, and you want to fill the big house with
Yeah,
Michigan, right?
I'm a big Michigan fan, so go blue. The big house holds 120-something thousand people. Can you imagine sitting in a VR experience, sitting in one of the seats watching a football game with the roar of an actual crowd around you? It'd be insane.
And you could look to your left and right and see other people and mix it with the people that were actually there, right?
Yeah.
So we see games in this new wave of immersive entertainment as a fantastic opportunity to continue some of the innovation that we're showing off here today at scale. So let's just bring it all together, right? We have all these real-world use cases that we have there on the left, and all these games use cases, and they are sort of the possible on the right. But what happens when we bring them together? We just put them all in the blender, and I'm going to create a virtual representation of the real world, where hundreds of thousands and even millions of people can interact simultaneously, a social experience with game-like elements that you can gather, connect, play, exchange, and experience together.
Did someone make a movie about something like that in like 1999?
They did, and they're remaking it shortly, I think. Yeah, it's still quite popular. But, right, here's my knockoff Matrix, if you will. I'm not exactly creating the Matrix, right? Not necessarily red pill, blue pill. But you've heard a lot about this concept recently, right? This is the metaverse concept. This is Tim Sweeney at Epic has talked about this at length. Facebook renamed an entire company because of this concept, right? And unfortunately, if you're expecting the announcement that Amazon is now Metazon, that's not on the next slide. But what we are looking to do is enable something that is truly big and expansive as something like the Oasis from Ready Player One, right? Where you have this central nexus that everybody can come together and meet, and then you have, branch out into different possibilities, different experiences, different games. Here's another example of this concept, actually. This one comes from Amazon Prime Video's show Upload. If anybody in the audience has seen it, it's actually quite funny. And I do recommend this. The second season coming out shortly. During this scene, the protagonist, unfortunately, has died, but his conscious has been uploaded to a virtual world. And he's asking, where are all the other dead people? Like, where are all his other dead compatriots? And he learns that he can only see 5 floors of this giant world at a given time. And then the person that he's talking to points over to the lake, and he says, there's 1 million people in that lake. You just can't see them, but you can tell they're there because the frame rate drops out. And so there's just some staticky here as this guy is moving or jumping into the pond. But what if you could do that, right? Well, maybe with some of the technology and some of the methods that we previewed here today, you would be able to see all 1 million people together. And so we're not really that far off from these metaverse-type experiences. In order to get there, it's going to take a lot of compute, right? This is a picture of a data center. It's a generic data center, because if I actually took a picture of an AWS data center, I would not be here. Not allowed to do that. But this is going to take a lot of computing power to execute on, because if you're going to have hundreds and thousands of or even millions of people connected and interacting together in real time, you need to be able to distribute that simulation across a multitude of servers to reach the scale that we're envisioning. And if that sounds familiar, if that problem statement sounds familiar, it's because it is. It's the exact problem statement that we were working on when we first started this crazy endeavor that we set out on, right? This was the 1 million independent and dynamic entities in a real world or virtual world setting that is capable of being interacted with, visualized, and analyzed by multiple users in real time. And so if you want to do something that is this kind of simulation at truly massive scale, you're going to need the cloud to do that. So over the last 45 minutes or so, we've gone on this journey to demonstrate and understand how customers like Wes and Lockheed are going from the game world of high-fidelity, real-time 3D engines and highly distributed computing frameworks to simulating the real world and creating these massive scale simulations with unprecedented scale and fidelity. But the session today here is just the start. It's a glimpse of the amazing things customers like yourselves and the audience will be able to build with AWS as we continue to explore how the cloud can change and improve the way that we do simulation and make it easier for everybody to do simulation in the cloud. Now, while it seems difficult, trust me, it's all about to get a lot easier to build and simulate with the cloud at this scale real soon. We have a lot more that we just can't wait to expand on and tell you in the near future. And so we invite all of you as customers and partners to engage with us to help move this forward. So from game world to the real world and onto the metaverse, at the end of the day, it's really just all simulation, right? And simulation lives here on AWS. Thank you so much for coming to our breakout session this afternoon. Hopefully we were able to keep you all awake and entertained, and perhaps you learned something. We'd love to take some questions, and we'll be here after to deep dive into some discussions if you'd like to continue the conversation. But once again, thank you very much, everybody. And please fill out the survey at the end. Thanks.